Okay, welcome to today's chat. Today we will be talking about Jupiter, the largest of the planets in the solar system. And this begins our discussion of the outer planets. Jupiter, Saturn, Uranus, and Neptune are sometimes called gas giants. I think that's a little bit misleading because most of their interior is composed of liquefied hydrogen and helium, and in some cases, ammonia, methane, and water. But these planets are certainly much bigger than the terrestrial planets, the inner planets, and the density is, appreciably smaller. But in any case, let's start with Jupiter. We'll go on to Saturn, and then finish up with the two outer planets. And yes, by the way, Pluto is not included in this discussion of outer planets because Pluto is not a planet. Okay, so basic properties. Again, it's the largest of all the planets. It's about 5 times further from the sun than we are, and it takes almost 12 years to go around the sun. One interesting thing with these very large planets is that during their formation, they actually accumulate a tremendous amount of mass, and through this, get quite a bit of angular momentum. So we find that a lot of these very large planets spin faster than these smaller planets, and that's true for Jupiter. Jupiter rotates with an orbit with a period of rotation of just about 10 hours. Now here's the interesting thing, or the amazing thing. While we think of Earth as being very massive, and certainly it's the most massive of all the terrestrial planets, it pales in comparison to Jupiter. Jupiter is 318 times the mass of the Earth. And because spheres, the volume of the sphere goes by the cube of the radius. Even though the radius is 11 times greater, the total volume of Jupiter is more than 1,000 times that of the Earth. So, very, very big planet. It would take, the equivalent of 318 Earths just to equal the mass of Jupiter. So we place them side by side, and certainly you can see that Jupiter, if it were placed by Earth, would overwhelm it in size. And again, Jupiter's density, just because it's composed primarily of hydrogen and helium, is going to be significantly less than the Earth. Jupiter's density is only 1.34. Just its immense size gives you a much larger mass. Jupiter's orbit, again, here's the interesting view when we look at the solar system. We look at it from above the plane of the orbits. We see that the inner planets are spaced very closely together, Mercury, Venus, Earth, and Mars. But then there's a huge gap between Mars and Jupiter. Mars is about 1.5 times further from the sun than we are. But then there's a tremendous jump going out to Jupiter. And really the outer planets were able to grow to these tremendous sizes because they really were well spaced out. The orbit's fairly round, very low eccentricity. Its orbital plane is only 1.3 degrees, so it's pretty much in line with the rotation of the solar system. It spins pretty fast, as we said, just about one rotation per 10 hours. If there were a surface on Jupiter to stand on, you'd notice that night and day would happen very quickly. Jupiter's axial tilt is only 3.17 degrees, so Jupiter really doesn't experience any significant seasons like the Earth and Mars do. Now, Jupiter's atmosphere is really the top of this huge envelope of hydrogen and helium. Where the atmosphere ends and the interior begins is sort of not a definite transition point. Really, I guess we would say the atmosphere ends where the gas becomes under so much pressure it becomes a liquid. But again, the atmosphere is mostly hydrogen and helium. If these were the only chemicals in the planet's atmosphere, we wouldn't see any clouds. We'd just see this big fuzzy ball. But the clouds are created by trace volatiles in the atmosphere, and these materials do condense, and they include, such things as water. We do have water vapor clouds, but other chemicals such as ammonia hydrosulfide and ammonia also create clouds. And these actually condense at lower temperatures, so they condense higher in the atmosphere. So when we look at Jupiter, Jupiter has no surface. What we're seeing is really the different cloud layers, the ammonia clouds, the ammonia hydrosulfide clouds, and finally the water clouds. And the one interesting thing is Jupiter's clouds show a much higher contrast than some of the other outer planets. And the primary reason for this is Jupiter's high gravitational pull actually makes the cloud layers much flatter and much denser than what we'd see in some of the other planets. Therefore, we see really good contrast when we're looking at the cloud tops. Like many of the planets, convection drives the atmosphere. The convection on the Earth is driven primarily by heat from the sun striking the surface of the Earth, and then that heat being transferred to the upper part of the atmosphere where the atmosphere cools. Jupiter doesn't have a solar-driven convection like the Earth does. The convection is actually due more to the interior heat, the heat left over from when it formed. And this source of heat drives the convection. Because of Jupiter's fast rotation, it is very strong in terms of its east to west flow. And this results in different atmospheric structures that we see in this picture, zones and belts. The zones being the lighter areas and the belts being the darker areas. Now, the zones are lighter in color because that's where the atmosphere is actually pushed upward, and therefore the cloud deck condenses at a higher altitude. It reflects sunlight much better. It's not as deep into the atmosphere, so there's not as much absorption. So the zones represent rising air. They are high-pressure systems. On Earth, our high-pressure systems generally rotate, just like the low-pressure systems do. And for the sinking air, the low-pressure air regions are belts. They're darker. They're just simply deeper in the atmosphere, so they're going to be darker in color. Again, when we're looking at the belts and zones, unfortunately, in this part of the PowerPoint, you can't see it. But, the belts and the zones are constantly in motion, and they move at different speeds, so therefore there's quite a bit of turbulence. Embedded in some of these, we also see some smaller storms, and we'll talk about the Great Red Spot, which is technically not a cyclonic storm. It's actually an anticyclonic storm. It's a high-pressure system, which is rising air rather than a low-pressure system, but it does rotate much like the hurricanes do on Earth. It's just high pressure instead of low pressure. The Great Red Spot is one of the few of these oval storms. You see some smaller oval storms which have white centers. It's one of these few of these oval storms which is red in color. There's now actually they call it the Red Spot Junior, which is a large oval spot. We think the very large storms get their color because they're dredging up chemicals deep within the atmosphere. And again, here's some just different images. There are some theories about why the Great Red Spot lasts so much longer than some of these other oval storms. Most of the other oval storms might last for a couple of months or a couple of years at most. But the Great Red Spot has been observed for hundreds of years. And it's now thought that perhaps this is driven by some type of heat plume coming from the interior of the planet. So that certainly would make sense. On Earth, hurricanes are driven by the evaporating water off the ocean. They're driven by the latent heat from the ocean. So the heat is coming from warm regions in the ocean. Here, we can imagine that the Great Red Spot could be driven by warmer fluid making its way up to the surface. And again, Great Red Spot is, a very easy feature to see on the surface of the cloud tops because it's about 2.5 times the size of the Earth. And again, there is this other long-lived storm that, again, we call the Little Red Spot or Red Spot Junior. Here on the right, we see the red spot, the Great Red Spot, and here we see, the Little Red Spot or Red Spot Junior. And again, it's thought that this storm was able to grow large enough to actually dredge up some of this interior material. We're not really quite sure what this red color is caused by. There are a number of different theories, and phosphorus is supposed to play some type of role, but some type of complex organic molecules are perhaps creating these colors that we see. Interestingly, Jupiter has lightning storms. Those water vapor clouds, just like they do on Earth, if they become turbulent enough, can generate lightning. And it's not it's not what you expect. You think that these big oval storms would be the source of the lightning, but instead, the lightning storms are probably caused by storms that resemble thunderheads or cumulonimbus clouds here on Earth. So it's not the big oval storms that are causing this. We have dropped a atmospheric probe into Jupiter's atmosphere. This is part of the Galileo mission, which studied the planet for an extensive amount of time. And this probe basically dropped into the atmosphere until it was finally crushed by the high pressures. And it actually detected less water vapor than we thought. But, reanalyzing its data seems to have shown that it might have been dropped into a very dry region where water vapor is just not as common. It was dropped into one of the belts, which is basically sinking air, and that could have had a drying effect and removing the water. Now, Jupiter's interior is composed of elements we're familiar with, but in states that are very unfamiliar to us. We look at the composition of Jupiter. It's about 3/4 hydrogen, about 1/4 helium, and a very small fraction of heavier materials, water, methane, rocky materials. And if we look at the interior layers, the atmosphere, which is in gas form, wouldn't be thick enough to be visible in this diagram. But the underlying layer right beneath the atmosphere would basically be liquid helium and hydrogen. Below that, however, Jupiter is so incredibly massive, and the gravitational pressure is so extreme that hydrogen and helium are actually compressed to a state that we just don't observe here on Earth, and that's the metallic state. Basically, hydrogen has 1 electron, helium has 2 electrons, and in a metal, the electrons are free. Well, if you place hydrogen and helium under enough pressure, the electrons actually do break free, and it behaves like a metal. What would this metallic hydrogen and helium be like? Well, first of all, it's at a much higher temperature than anything that we see here on Earth, but its electrical properties would probably be very similar to Mercury. I guess at the interior temperatures, we're looking at the mantle, which up to the atmosphere is about 200 degrees Kelvin, but it goes up to 10,000 degrees Kelvin. It's basically as hot as a blue-white star. So, if you actually to visualize some of this material, it would probably look more like very, very hot molten metal. Again, the mantle is either liquid hydrogen and helium or metallic hydrogen and helium. The core we really don't know much about. According to models, it should be somewhere between 20,000 and 40,000 degrees Kelvin, which is about as hot as the hottest surface of any star we know of. And due to this extreme heat, we're not quite sure if the core ever differentiated, that the heavier material ever had a chance to settle to the bottom, like the rocky material, and the lighter material, like the water, would go up. But at these pressures, even though it's at 20 to 40,000 degrees Kelvin, any water there would actually be a solid. Technically, it would be ice, but it would be ice that is so incredibly hot that it would, again, shine very brightly, brighter than the surface of the sun. And if you took a piece of it, it would explode if you freed it. Now, the terrestrial planets, their interior heat was due to radioactive decay. In Jupiter, radioactive decay really doesn't play a very large role. Jupiter formed very hot, and it's still, even after 5 billion years following its formation, it's still cooling off. So the interior heat is left over from its formation, and it actually radiates more heat outward than it receives from the sun. If we look at it in an infrared photograph, we can see, especially in the regions where the air is sinking, where we have those belts, it is radiating quite a bit of energy into space. Jupiter has a very intense magnetic field. The magnetic field is 20,000 times more intense than that of the Earth. And while the Earth's field is generated by, convection currents within the outer core, it is the metallic hydrogen and helium which is responsible for generating Jupiter's very intense magnetosphere. Only the sun's magnetic field is stronger than that of Jupiter. Interestingly, because Jupiter has a very volcanic moon, Io, orbiting near it, Io is constantly spewing elements into space, and these elements are actually trapped as ions in Jupiter's magnetic field. So this creates a very, very intense radiation belt. If humans were to venture into this radiation belt without any shielding, the radiation would kill them. The strong magnetic field and the ions released by the moons orbiting Jupiter result in a very strong aurora. Now, on Earth, our aurora is generated basically by particles which come from the sun and then are trapped in the Earth's radiation belts, and then they make their way down to the poles where the magnetic field reconnects with the planet. In Jupiter, these auroras are pretty much independent of what the sun is doing. Again, the ions can be from the moons and are essentially trapped, once again, by Jupiter. Here's an interesting picture of the aurora on the poles of Jupiter. And it really shows that there's a strong electrical connection between the moons and Jupiter, through the magnetic field. Here you see basically a stream of particles coming in from Io, and then the other planets also, Europa, Ganymede, and Callisto is too far away to be that connected that we'd see it. So that's Jupiter itself, very impressive planet, extremely large, composed mostly of hydrogen and helium, and in fact so incredibly large that it's still cooling off from the time at which it first formed. Now let's talk about its moons. Not only is Jupiter interesting because of the planet itself, its moons actually make it a very interesting system to study. And in terms of Jupiter's moons, really the only important ones, I think, for our study are the Galilean moons. These are the 4 big ones. But it is important to talk about some of the other moons. There are these inner moons which didn't form that close to Jupiter, but are probably fragments of either moons that were destroyed or asteroids. There are 2 sets of outer moons. There's a set of outer moons that rotate with the spin of the planet, and they're called the prograde outer moons. And those, rotating in the opposite direction. But honestly, if you want to talk about the moons that are the most interesting, the moons that are worth studying, that would really be these Galilean moons here. Okay. Again, talking about the inner moons, nothing much to say about them. Small fragments. In many cases, they look a lot like, Mars's captured asteroid moons, Phobos and Deimos. The largest of them is Amalthea, but even that is just too small to pull itself in its spherical structure. The moons actually orbit within the ring system of Jupiter, so perhaps I guess you didn't know that Jupiter had a ring system. It's very, very tenuous. But perhaps some of these moons are the source of the rings. The rings are so tenuous, they're so low in density that really the only way to see it is to go behind Jupiter and see the backscattered light. So it's made of very small, thin, dark material. And again, because they're only visible from the back of the planet, meaning that they strongly forward scatter the light, the particles have to be only about a micron or less. Now again, the important moons are the Galilean moons. These moons are comparable in size and mass to some of the terrestrial planets. They were discovered in 1610 by Galileo using his telescope. And when we look at the mass of the different moons, we see that Ganymede, the largest moon in the solar system, also has most of the mass. Callisto is the outermost. It's slightly smaller than Ganymede. And then comes Io, and the smallest is actually the most interesting, Europa. Now, one thing we should understand is that 3 of these Galilean moons are actually in resonance with one another. They orbit such that every time Io goes around, Europa makes a half orbit. Or I should say every time Europa goes around, Io makes 2 orbits. Likewise, Ganymede orbiting further away makes 1 orbit for 2 orbits of Europa and 1 orbit for 4 orbits of Io. This means that they're constantly interacting at the same place in their orbits, and therefore this resonance creates tidal heating within the different moons. Now, the Galilean moons, we think, most likely formed around Jupiter, almost like a miniature version of the solar system. And because of Jupiter's very massive size, Jupiter probably radiated enough heat to cause most of the volatile materials, such as the ices, to be driven toward the outer part of the disk. And that's why the innermost moons have less ice than the outermost moons. Even more interesting, computer simulations seem to tell us that these were not the first batch of moons that might have been forming. Simulations show that several generations of moon might have gone by as Jupiter was growing in size, and that the current Galilean moons were just the last or most recent set of moons that survived. Some simulations show that as many as 5 generations of moons might have formed, where this last set was created when Jupiter's finally stabilized. Now, where do all these moons come from? Once again, the Galilean moons probably formed a lot like the planets that formed around the sun. In this case, the process of formation would have been, just through accretion. Accretion. That as the disk material clumped up, pockets then formed these moons, and we ended up with 4 large Galilean moons. The other moons that we see are probably fragments of asteroids, fragments of comets, things that just got too close to Jupiter and eventually got caught in its gravitational field. Here's a diagram of the orbits of the outermost moons. Again, we have the inner outer moons, if we want to classify them that way, which basically orbit with the rotation of Jupiter. And then you have the retrograde moons that orbit in the opposite direction. So again, the fact that we have these prograde and retrograde sets of moons indicates that there's a lot of material that was probably captured by Jupiter, over time. The prograde moons probably settled closer to Jupiter, since prograde orbits are more stable, and the retrograde orbits settled further away, where they're less likely to be influenced by the other moons. Okay, so yeah, you're going to hear a lot of times that Jupiter just has a very large number of moons. But in all honesty, most of these moons should be considered to be nothing more than debris. Unless the moon is large enough, it's not going to pull itself into a sphere. And as we saw, Amalthea, which is one of the largest of the small moons, looks pretty much like a chunk of asteroid or something. So let's talk about the 4 Galilean moons and look at them. Callisto's not all that interesting. Yeah, it's big. It's got a lot of size. If we were to say that it's interesting, we'd probably say it's interesting because it gives us a nice view of what the solar system might have been like at one time. We see a surface which in many ways looks a lot like the surface of our own moon, in that there are a tremendous number of craters. The difference here is that when we look at Callisto, we're actually looking at a big ball of ice, and the dark material is really the dust left over from impacts of micrometeorites and things like that. In size, Callisto is bigger than our moon. It's still considerably smaller than the Earth. And, in terms of radius, the Earth is it's about 38% of the radius of the Earth. Again, the surface is covered with water ice, tons of impacts, and it would look very bright white if it weren't for the constant rain of micrometeorites on the surface that darken it. We look at the surface, and because it shows evidence of so many impacts, we know that it probably has not been geologically active for a very long time. The surface of the moon has no atmosphere, so the ice is constantly subliming, and this sublimation is probably the only geological process that causes any surface features to erode. We do see interesting ice formations that are similar to what we see on Earth. Things such as sun cups appear to cover some of Callisto's surface. We see these on the Earth where large sheets of ice are melting in the sun's heat. Probably the most impressive feature is something called Valhalla, which is seen to the side right here. It's a large impact basin that was created by most likely a large comet or asteroid slamming into the surface. Like Chloris Basin of Mercury, if you look on the opposite side of where Valhalla occurred, we see at the antipode jumbled surface, just like we see on Mercury. With respect to Callisto's interior, we're not quite sure if it's fully differentiated. We know that ice has at least settled in a layer above any interior rocky material. But at 1.79 times the density of water, it's pretty clear that Callisto is a mixture of ice and rock. Callisto never really is thought to have become warm enough to differentiate where all the rock would have settled to the center. So, the interior may have a thin layer of water or slushy ice, but we think what we see here is a thick layer of ice covering a thin layer of water or slush, and then a mixture of rock and ice underneath that. Going from the outer to the inner of the Galilean moons, Callisto is the furthest out. Ganymede is the largest moon in the solar system. It is bigger than Callisto, and the interesting thing is, in some respects, we see a lot of ancient cratering like we see on Callisto. However, the surface is covered with these grooves, which indicate that the crust of Ganymede at least was under some tension and compression. Again, Ganymede being the largest moon in the solar system is actually even larger than our own moon. Its mass is more than twice as much as the moon, but even at that, it's only about 2.5%, or about 1/40th the mass of the Earth. It's actually larger in size than Mercury, but Mercury is still more massive because Mercury is made more of iron, while Ganymede's made mostly of ice. In any case, the surface of Ganymede, again, dominated by a lot of impacts, but it also has these surface features that seem to indicate that the crust has been stretched, and this might have been from the tidal interaction with the other moons. Again, not plate tectonics, but sort of tectonic activity from different tidal effects have probably distorted the crust. We believe the interior of Ganymede is composed of a thick layer of ice. There might be a outer mantle of water, or more likely slushy ice. And then, due to Ganymede's large size and some of the interior heating or tidal heating from the other moons, we think that there's probably a rocky outer core and a metallic inner core. So Ganymede, just interesting because of its sheer size. Some geological activity on it, probably not that recent though. But, in terms of what's happening inside, there's probably enough heat to at least keep some of the water in a partially liquid state. Not enough water, close to the surface to, support life as we understand life, but interesting nonetheless. The next two moons are probably the most interesting. Save the best for last. Europa is the smallest of all the Galilean moons. But it's also the most interesting because when we look at Europa, we right off the bat see something strange is going on. Europa's surface is, very reflective. Unlike Callisto, which is sort of dark because it's covered with dust from impacts, Europa's surface seems to be fresh. It seems to be new. There are few impact craters on it. Again, it's the smallest of the Jovian moons. It's even smaller than our own moon. about 91% of the radius of our moon, but it's considerably more dense than the other two outer Galilean moons. And the surface is a thin layer of ice, thick by our standards. It's probably a couple miles thick, but it's covered with these fractures and these faults, and it's most likely that the tidal flexing from both Io and Ganymede not only constantly fractures the surface, but also creates interior heat that keeps the water below the surface liquid. And again, you can see there's a tremendous amount of faults, like the tectonic faults that we see here on Earth. But again, these are probably due more to tidal flexing than convection in the mantle. Again, what is interesting about Europa is in many respects, it's not all that unlike the Earth. There is a metallic core, there is a rocky mantle, and then there's a thin layer of water, which is then covered by an even thinner layer of ice. So this is of great interest to us because if this water is liquid and we have this interior heat from tidal flexing, we have all the ingredients that we need for life. We believe that some of the first primitive life on Earth probably started at the bottom of the ocean near undersea vents. With all the tidal flexing, heat is probably released the same way into these European oceans. So again, we have the conditions for life. Whether or not life existed, we have no way of knowing. Okay? We would actually have to visit Europa in order to discover life. So Europa is, really of great interest because, it's one of the few places in the solar system that actually has favorable conditions for life, even more favorable than Mars in its current state. If you want to visit a place that's very unfavorable for life, go to Io. It's the most volcanic body in the solar system. Io experiences so much heating from the gravitational tides that any water has been driven out long ago. Essentially, what we have left with Io is a body that's even hotter in its interior than the Earth. And its surface is free of impact craters, but instead what we see are a lot of caldera, a lot of volcanic craters, which constantly repave the surface. Again, here you can actually see, here's one of the volcanoes that was recently active, and you can even see a ring of sulfur-like material that's been deposited on the surface. Very interesting color. A lot of the color that we see on the surface is due to elemental sulfur and other compounds of sulfur. Reds, oranges, yellows, even white. If you heat and then rapidly cool sulfur, even in its elemental form, you can get a lot of these very interesting colors. Now, due to Io's low surface gravity and the lack of atmosphere, when these eruptions take place, and you can see, here's an eruption taking place. Here on Earth, when eruption takes place, we have magma that comes out as lava. We also have a lot of volatiles which escape up to the atmosphere. We see the same thing here on Io. There's a big plume of material being launched into space, and these plumes on Io, really put a lot of material into this large torus within the Jupiter radiation belt. Now again, Io is interesting to study because its lava is actually hotter than the lava we see on Earth, even the hottest lava on Earth. Found in places like the Hawaiian Islands, do not reach the temperatures that we see on Io. So when we're studying the volcanism on Io, we're actually studying volcanism that may have been very common on the Earth, a long, long time ago. So, here is an actual image of one of these lava lakes. And you can see, this lava lake is not actively erupting. You see thicker crust of rock, and then you can see thinner layers of this almost like, very dark rock. It's, what we expect at some of these higher temperature eruptions. We expect a very dark basaltic rock. Here's some images that are combined visible and infrared images of eruptions that are happening at different times. Here's the same volcanic complex. Here we see sort of a eruption out of this caldera, and the infrared light, really shows where the lava is coming out. Remember, there's no atmosphere. When this lava comes out, it quickly radiates and cools because there's nothing to keep it warm. And then here you can see this fissure right here is erupting. And once again, during these eruptions, we typically see a plume of material which is blown upward. A lot of the material rains back down, but some of it does escape into space. And if you look around this eruption, here's the plume, and then here's the flow of the hot lava leaving the flow. And you can see lots of sulfur dioxide being given off by the cooling lava, even as it hardens. Io does have some mountains. This is important because it seems to indicate that at least the interior is partially solid, unless Io was, if Io's mantle was completely liquid, two problems would happen. One, convection would go so rapidly, it cooled the mantle so quickly that it would have to become solid or semi-solid like we see on the Earth. And two, it couldn't support mountains. Mountains would just simply sink into the mantle. So, we do know that its interior at least has a partially molten mantle. And, like the Earth, we believe it would have an iron core. The heat would allow for differentiation, so the heaviest material would be able to collect at the core. And again, there's another view of a mountain. This mountain somehow is associated with, volcanic activity, because we can see the white sulfur frost, which has been being sprayed all around the base of it. Well, let's go back and talk about some other things. So, again, the Galilean moon system around Jupiter, the Jovian systems of moons, are really interesting. The Galilean moons have a very large old moon in Callisto orbiting far from Jupiter. Closer in, we have the largest moon in the solar system, Ganymede. And the two most interesting moons are sort of like heaven and hell. Europa might be heaven for life in terms of it supports the type of ocean that would be hospitable for life to live on. There are some questions about the salinity of the ocean. It might be too salty for life as we know it, but certainly it's exciting because it gives it the possibility that life could exist. And of course, we have Hell, which is Io, which is a tremendously active volcanic system, the most volcanically active system in the solar system. You wouldn't want to be near any of these volcanoes when they erupt because the lava is much hotter than the lava that we see on Earth. But to make matters worse, the radiation levels on the surface of Io would be almost instantly lethal to most people. Let's wrap up Jupiter by talking about a very interesting event that happened. This was Shoemaker-Levy 9. It was a comet, which is once one solid fragment, which collided with Jupiter and broke up into several small pieces. And here we can see all those pieces. As he impacted the surface of the atmosphere, they left some very interesting marks. Now, remember, Jupiter has no surface. So therefore, if something hits it, no mark that's left is permanent. You can't leave craters. But on impact, we did see huge fireballs created by the impacts. And then what was left over were these little dark smudges. And these dark smudges may have been the material from the comet being vaporized and then recondensing in the atmosphere, or other material dredged up from the atmosphere. It's probably mostly cometary material, simply just stained the atmosphere a little bit. Okay. I said that would be the last. I just want to quickly mention some things. Jupiter has actually been visited quite a bit. What we know about Jupiter originally came from two space probes that flew by, Pioneer 10 and 11. They gave us our first close-up images of Jupiter. But then Voyager 1 and 2, which are much more sophisticated, allowed us to really study the planet in depth. Although Voyager 1 and 2 were flybys, they went on to Saturn soon afterward. We were finally able to put a satellite in orbit around Jupiter, and that was the Galileo mission. And obviously, because the Galileo mission spent years around Jupiter, it was able to study the planet for a very extended period of time. And again, much of what we know about the planet now is thanks to the Galileo mission. Interestingly, we actually destroyed Galileo, the space probe. The fear was that it might have had some bacteria from Earth, which could have contaminated one of the moons. So if life existed on, let's say, Europa, and Galileo crashed into Europa, there's a fear that we could contaminate the planet and disrupt whatever ecosystem was there. Again, we have no idea if anything exists on Europa in terms of life because, we haven't investigated enough. It's just speculation. But nobody wanted to take the chance. So when the Galileo mission ran out of propellant, it couldn't maneuver anymore, they finally sent it crashing into Jupiter. The Cassini mission, which went on to Saturn, did do a flyby and did study Jupiter a little bit. New Horizons, which is on the way to Pluto, did the same. But, we haven't had any visitors to Jupiter right now. Nothing currently orbits it. There was a planned mission called JIMO, the Jupiter Icy Moon Orbiter, that was supposed to study the moons of Jupiter. That was scrapped because of large costs. But currently, Juno is on its way to the planet and will arrive there in 2016. There are some proposed missions to Jupiter. There's supposed to be this Europa Jupiter System mission, which would be funded by NASA, ESA, which is the European Space Agency, and Russia and Japan. But it probably won't be launched for a very long time, again, due to the funding. Okay, let's summarize. Jupiter, largest of the planets. the most massive planet in the solar system. And in fact, if you took Jupiter and compared it to all the other planets, okay, you put Saturn, Uranus, Neptune, all the inner planets on another side of the scale, Jupiter still would outweigh them, okay? Jupiter is almost 3 times more massive than all the other planets put together. We have a very intense magnetic field around Jupiter. Jupiter is made of mostly hydrogen and helium. And deep in its interior, we have this material at very high pressures where it becomes metallic. We don't know the core structure and composition, but hopefully the Juno mission will help answer some of that. In terms of the 4 large moons, the Galilean moons, Callisto is old, relatively undifferentiated, geologically inert. Ganymede is the largest moon in the solar system. But again, the 2 most interesting ones are Europa. It's very similar to Earth. It is a vast subsurface ocean with, and we speculate, the potential to support life. We have no idea what's down there, so we're just speculating. And finally, Io is the most volcanically active body in the solar system. So that wraps it up for Jupiter. So of course that means we have to go on to our next outer planet, and that is Saturn. We of course know Saturn to be the ring planet. Saturn's not quite as massive as Jupiter. The basic properties are it's a little less than a third as massive as Jupiter. The strange thing is Saturn is almost as big in size. And because it's much less massive and almost as big in size, it is very low in density. When we compare Saturn to the Earth, again, the Earth is really dwarfed in size. Saturn is about 100 times larger in mass, about 840 times larger in volume. And if we could take Saturn and put it on a huge ocean, it would actually float. Saturn orbits at nearly twice the distance that Jupiter orbits. So when we get out to Saturn, it's actually considerably colder by Saturn than it is around Jupiter. You know, every time you double the distance, you actually get 1/4 the amount of sunlight. So, you know, very, very cold out there. Unlike Jupiter, Saturn does have an appreciable axial tilt. It does rotate about every 10 hours, like Jupiter. But with an axial tilt of 25.3 degrees, it experiences seasons just like we get here on Earth. Atmosphere, very much identical to what we see on Jupiter, just not as much gravitational pull on it. So the cloud tops are less compressed. So it's harder to see things like belts and zones on Saturn. Interestingly, near the poles, we actually start seeing a bluish hue. And this is due to the fact that the small traces of methane, which are in the atmosphere, tend to absorb red light and tend to scatter the blue light. And of course, you know, this gives it sort of a bluish hue in the polar regions. But like Jupiter, most of the color that we see is actually from the materials in the cloud tops. Like Jupiter, there are cyclonic storms. They're harder to see because of the haze and the less compressed cloud tops. We do see lightning, and really the strange thing about the planet is there seems to be, I don't know if you can even call it a storm, but there's a large spiral-shaped vortex of air that sits right over the pole. And images of this have shown very complex shapes. I don't know if you can see this very well, but clearly you can see a hexagon on this, and very subtly, if you look at this image right there, So, this vortex, which occurs at the poles, is very interesting. Again, Saturn's interior is about the same as Jupiter, same composition. The layers are a little bit arranged a little bit differently. Again, not as much gravitational compression. Therefore, the layer of metallic hydrogen and helium is actually much deeper into the planet. So we don't have quite as strong of a magnetic field, but the magnetic field is still much stronger than what we see on the Earth. Again, the mantle and the core are probably composed of ice and rocky material. The interior of heat from Saturn is less than that of Jupiter, but still there's quite a bit of heat left over from the planet's formation. Again, the magnetic field, not quite as intense as Jupiter's magnetic field, but we do have particles trapped in a radiation belt. Like Jupiter, we have this region where the radiation is very intense near the planet. Again, auroras, we see auroras, due to the interaction of the magnetic field with these trapped particles. Okay, the rings. Everybody knows Saturn for its rings, but the rings really are not directly associated with the planet itself. The rings are orbiting debris. Okay, they're not touching the planet; they're orbiting debris. They're like little satellites going around the planet, and we don't know where this came from. Maybe a moon got too close. Maybe the material is just left over from its formation. But we're really not sure even if these rings are permanent or whether they're a transient structure. Again, one theory is that more moons or comets got too close to Saturn, disintegrated, and formed the ring. But maybe the rings just formed were too close to the planet where moons couldn't form. We're really not sure. All the outer planets do have rings. It's just that Saturn's rings are the most prominent. Now, the densest rings are the ones that we see. We categorize the rings according to, we label the rings according to letters. The first two rings discovered were the A and the B ring, and then less dense is the C ring, and then there's a D ring even closer to Saturn. Basically, these rings are, again, particles of ice and dust that orbit the planet. Here's a look from behind Saturn, and we can see all the different planets. If we view it from the backside, we can see that the dense inner rings are visible, but we also see these outer rings like the E ring, which is thought to be from the moon Enceladus. Spectroscopic studies of the ring indicate that the A ring has the largest particles, the B ring the second largest, and all the other rings have very small particles. Spectroscopic studies have also indicated that the rings are dominated mostly by ice, but there is some rocky material. Here in this ultraviolet picture, we see the blue representing the large ice concentrations, where red represents mainly dust. So again, rings, they're beautiful, but it's basically just material that's been trapped in orbit around Saturn. If you look at the total mass of Saturn, the rings are an insignificant fraction compared to the mass of Saturn. In terms of the moons of Saturn, there is one large moon and then a lot of smaller medium moons. Here's a side-by-side of some of the largest moons. Only Titan is considered to be a moon of significant size. The other moons, Iapetus, Rhea, Dione, Tethys, Enceladus, Mimas would be quite small, compared to the Galilean moons. Jupiter had no medium-sized moons. It only had the 4 large moons and then a lot of small moons. But Saturn sort of has a mix of, large, medium, and small. Large being Titan, everything else being medium, shown on this page, and then much smaller. So again, what we see is the moon's broken into several categories. There are moons that actually orbit within the rings of Saturn and keep the rings stable. The inner moons are medium-sized. Mimas, Enceladus, Tethys, and Dione are medium-sized moons that orbit outside the ring, but still fairly close to the planet. The outer moons tend to be the larger moons. Rhea and Iapetus are medium-sized moons, and of course Titan is the largest moon. And then there are a lot of outer moons that are simply just, irregular and probably captured comets or asteroids. Again, the ring moons. Here's a representation of what the ring moons look like. It has this bizarre shape because it actually accumulates particles on its equator because it bisects the planet. Because it bisects the rings. But again, these little moons or moonlets are very important for keeping all the particles in line. Here we see what's called a shepherd moon. It actually keeps orbiting and forcing the particles to maintain a very sharp orbit. Here's an interesting pair of moons. These are 2 shepherd moons called Prometheus and Pandora. One of these satellites or moons orbits on the inside of the ring. The other one orbits on the outside of the ring. And they keep the thin F ring very well structured. Here's one of those strange moons that orbits within the ring system, and you can see material clumping up on its equator. But this moon Pan actually orbits in what's called the Nike gap. And nobody understood why this gap existed until we discovered this moon. So let's look at some of the inner moons. Mimas is interesting if you're a Star Wars fan, because when it was first seen, everybody thought it looked like the Death Star due to this large impact called Herschel. And Mimas is responsible for the gap in the rings between the outer A ring and the inner B ring. Mimas orbits once for every 2 orbits of particles in this Cassini gap, so Mimas really acts to clear that orbit out. Now Enceladus is really almost as interesting as Europa. Like Europa, it may have some liquid water below its surface. Its surface is very young, few craters, and we're really not sure what's heating the interior, but something is heating the interior enough to cause large fractures and other tectonic-like structures on the surface. This false color image shows fractures in the surface, what we call the tiger claws, or tiger stripes, where we think the surface is fractured and liquid water actually makes it to the surface. The discovery of liquid water was made indirectly by the Cassini mission, which is currently orbiting the planet. And as Cassini orbited through the magnetic field, it noticed a distortion in the magnetic field every time it passed Enceladus. Now we know that this distortion was due to a plume of water vapor which neutralized the particles in the magnetic field, bending the magnetic field lines. Cassini also measured the occultation of a star and noticed that the star didn't abruptly decrease in brightness. It actually took a while to decrease in brightness, indicating a very tenuous atmosphere. Finally, this image confirmed the presence of these geysers of water vapor. And in this image, we can clearly see the geyser. And in this colorized image, we can see enhanced contrast. So Enceladus does seem to indicate, or we have indications that there is liquid water below the surface of Enceladus, because it is spraying this water into space. And even thermal measurements seem to show that these fractures are much warmer than the surrounding environment. Here's another thermal image. And it seems like there's some heat source near the south polar region where these tiger stripes are, which is powering this. The problem that we have is we don't have a good mechanism to heat Enceladus. Enceladus is very small. Radioactive heating shouldn't be enough to warm the water where it can create these geysers. Likewise, orbital resonances, like we see heating Io in Europa, don't occur on Enceladus anymore. It may be that Enceladus flipped its spin, and through this spin flip, in interaction with some of the other moons, it was able to heat enough of the water to create this hot spot. But what do we know? Enceladus, much smaller than Europa. Its warm region producing these geysers is very much isolated to the southern part of the moon. So it's really sort of a mystery. Could life exist there? We really don't know. It might be possible, but the presence of liquid water always gets us thinking. The other moons. Tethys, basically a big ice ball. It is an icy layer covering probably a rocky interior. It does have a huge impact on it, even bigger than what we see on Mimas by ratio. And the strange thing is, Tethys is actually co-orbiting with two other smaller moons. These smaller moons are at what are called the Lagrange points, Telesto and Calypso. Dione is the fourth largest. What was Tethys? Tethys was the fifth largest. Dione is the fourth largest moon. Again, big ball of ice, lots of impact craters, meaning that it's very old. We do see some strange wisps on the surface, which are probably fractures. But again, these probably are very ancient features. Well, Enceladus was the most interesting of the inner moons. Of the outer moons, we have Rhea, which again is pretty inactive. It's the second largest of Saturn's moons. Many impact craters, some wispy fracture features like we saw in Dione. But a close-up shows that the surface is very old, and actually the surface is kind of reddish. This is due to hydrocarbons on the surface, which have been hit by the ultraviolet light from the sun. Saturn really only has two moons that are very interesting. Enceladus is one of them. That's a big mystery. Where is this liquid water coming from? The other interesting moon is Titan. It's the second largest moon in the solar system. But here's the thing. It's the only moon with an appreciable atmosphere. So its atmosphere is high density. It's about 60% denser than our own atmosphere, about 50% higher in pressure. But unfortunately, Titan, although it has a lot of the same chemistry that we have here on Earth, Titan is extremely cold. Its atmosphere is primarily made of nitrogen, just like our atmosphere is, and there's smaller amounts of methane, about 10%, and it's this methane which creates smog. You've heard of photochemical smog here on Earth. In Los Angeles, it's a real problem. Not as much of a problem here, but it is a problem in the New York area. And what happens is pollution, organic pollution, is reacts with sunlight, and this creates these smog particles. Same thing happens in Titan. The methane reacts with the ultraviolet light from the sun and produces larger particles. If we look at Titan when it's backlit from the sun, again we see the atmosphere is really quite thick for the size of this moon. Again, the haze is created by photochemical reactions, and it actually makes it impossible to see the surface of Titan in visible light. Here's some more view of some of the haze. So when we sent Cassini, the space probe, to investigate Saturn, we had the problem where we couldn't see the surface directly. However, the smog particles don't block infrared light as effectively. So in this infrared photo, we can see some dark regions and some lighter regions. And what's interesting is Titan has highlands and lowlands just like we have on the Earth. But again, it's so incredibly cold that all the temperatures correspond to very different processes than we have on Earth. On Earth, molten rock is a source of volcanism. On Titan, we think that the surface is basically ice, and when the ice gets warm enough, it erupts just like a volcano. So we have ice volcanoes on Titan. On Earth, it's warm enough that water is a liquid, but on Titan it's so cold that actually methane, the primary component in natural gas, is a liquid. So we have lakes. We have, in this case, this lake's as big as Lake Superior, not of water, okay, but instead of liquid natural gas. So if you were to visit Titan and the temperature weren't a problem, in many ways it would look like the Earth. Rock formations would be made out of ice. Ponds and lakes would be made out of methane. But again, the temperatures are extremely, extremely cold. Here's an impact crater on Titan. We don't see very many of them, indicating that it's quite geologically active. And we actually landed a space probe on Titan's surface. It's the only visit that we've ever made with a lander on the surface of a moon, other than our own moon. And as this Huygens probe was making its way to the surface, it used a parachute to slow its descent. It took images, and many of the landforms look just like what we see on the Earth. This right here is a canyon cut by methane, methane rain and methane rivers, and cut a channel into the ice. Here's another picture. I mean, this looks like it could be like off the coast. Here you see, sort of rocky features. Here you see what looks to be like the ocean. In this case, this ocean really is actually a dry lake bed. And when Huygens landed on this dry lake bed and took this image. You see many rocks here. These rocks are actually particles of ice. And as it landed, it sort of sensed that the surface was squishy, like it was wet. Again, here's another image of Titan. This was taken with infrared light, and we can see dark and light regions. The lighter regions are the highlands. The darker regions are probably things like dry lake beds. And Cassini was also able to use radar to detect large lakes. And again, during the descent, we see a lot of features that look like river valleys. Here again is the haze layers. Again, what we think happens with methane is the methane plays the same role as water does on Earth. So, when looking at this, not only do we have a haze layer, the methane does condense into clouds, and the methane will then rain down in liquid form to the surface, where it can collect in these different rivers and lake forms. And here are just some of the chemical reactions that take place with ultraviolet light, producing some of the heavier elements that we see. Now the question is, because Titan has so many similar features to what we see on Earth, rivers, lakes, a liquid rain system, could life exist on this moon? And the answer to that is probably not. The temperatures are probably just too cold to support biological reactions that are essential for life. Here's one of the other moons. This is Iapetus. It's Saturn's third largest moon. And the interesting thing about this moon is, like the others, it's just a big ball of ice surrounding a rocky core. But on the surface, we see that some of the surface is covered with dark material. Here's a large impact basin, by the way. And some of the material is covered with lighter material. Not covered with lighter material. Some of the surface is not covered with this dark material. It's just very light. We think Iapetus, as it orbits Saturn, its leading edge picks up this dark material given off by the other moons, whereas the trailing side of Iapetus is relatively free of the dark material that's coating it. Again, there's a close-up. Again, the trailing region is pretty much free of this debris. So it's sort of like driving your car through a rainstorm. Most of the material ends up on the windshield, whereas the back window sometimes can be completely clear. It's like Iapetus is going through this rain of dark material, so sort of covers one side, not the other side. Finally, Saturn has some other moons. They're actually given interesting names: the Inuit group, Gallic group, the Norse group. These are all very small. The largest of these is Phoebe. And what's interesting about this is it's probably a captured Kuiper Belt object, probably formed out by Pluto. Its orbit was disrupted, and then it made its way into the Saturnian system. So again, summarizing Saturn, very similar in composition and structure to Jupiter. It's the most complex and extensive ring system, or it has the most complex and extensive ring system of all the planets. And there's many moonlets and shepherd moons. Titan is the second largest, and it's basically just a cold analogy of Earth.